Okay, sorry, welcome back. This is 14.5 on surface area. Okay. And what do we, sorry, just have to clear my throat there a bit. Okay, so what's the deal here? What are we doing? I'll have some surface in 3 dimensions. You know, always use like a hemisphere or something. Okay. And we want to find the surface area of this figure. We can standardize it into XYZ plane, you know, and then we'll assume it's inhabiting a 3-dimensional space over top of some region R. Okay. Something like that. Then we can, so how is this going to work? Well, we're going to pick out a point in the region, kind of go up to the surface here, and at the surface, we're going to attach a mini plane, you know, like a little, I don't know, a little rectangular area place that we can figure out the area of that little rectangle. Okay. Okay, so what we're going to end up doing is adding up the area of all these little rectangular, they're kind of like tangent planes. I guess you could say they're tangent planes if you wanted to. And if you add up all the areas of those little tangent planes, you get the surface area. And the end result, it kind of looks like a disco ball. You know, it's a bunch of little squares attached to the surface, and you're finding the area of all those little squares, adding them all up, and doing your limit process. And that gives you the surface area. Okay. So the question becomes, how the heck do I get these little rectangular regions, and then how do I find the area of those little rectangular regions? Well, we're going to use vectors to do that, and it's kind of leading into the vector calculus that we'll be looking at in section 15. Okay, so given any point in this region down here, the circular region, we'll be able to determine a vector going in the direction of the x-axis and then a vector going in the direction of the y-axis. Okay, in particular, having kind of this small magnitude. In particular, then you'll in this direction you'll have some change in x, and then back here in this other direction you have some change in y. Okay, those two distances we'll use to describe the vectors as well. So let's call this vector in the direction of the x-axis u, and this vector in the direction of the y-axis v. Okay. So u will be the vector. Well, I want to go by change in x in the x direction. So my first component is change in x. And the book will probably put like change in x sub I, just in case these have varying widths, which they can. And then in the y direction, I don't want to move. So I just want this vector to be in the x direction and perpendicular to this vector in the y direction. Okay, so I'm going to say 0 here. And then there's going to be either a dip or a jump, right? So I'll have, with regards to this vector, slope, right? If you take the partial derivative with respect to x, so in particular the partial derivative of f with respect to x, that tells you a slope, a rise over run in the x direction. And that in particular will be the slope of this little vector here that we're after. Okay, so it'll be a rise over run in the x direction. Okay, so for the third component, which we basically need to know how much to go down or how much to go up in the x direction, we're going to use this partial derivative. But we don't need the run part, we just need the rise part. So what you do is multiply the partial derivative with respect to x times change in x. Okay, and that will give you just the rise, because the runs will kind of divide out. Okay. Okay, so that's our first vector in the u direction. Then our second vector in the first vector was in the direction of x. Our second vector in the direction of y, which will be perpendicular to that first vector, and therefore kind of describe this little square or rectangle that we want to find the area of. For this vector, then, we don't want to move in the x direction. We want to go change in y in the y direction. And then in the z direction, again, we want to know that slope in the y direction and use that, right? So again, this is rise over run in the y direction. And so for that component, I'm going to use the partial derivative of f with respect to y times change in y. Okay? And that gives us the vectors that we require to describe this rectangle. Now all we need to do is figure out what the heck is what the heck is the area of this rectangle. Okay. Okay, so this comes from chapter 11, which we've probably all forgotten by now. But in particular, it's the area of the rectangle described by two vectors, u and v. So the area in particular is a parallelogram, but we could say rectangulars in general. The area here is going to be equal to the magnitude of the cross product. Okay? And again, this is just a formula that they give you, and lists of formulas with regards to the properties of cross products. That was in section 11.4. Okay, so this is 11.4 stuff that we've forgotten. Okay, so if you do the calculations using these u and v as your vectors, you can literally do the cross product and then take the magnitude. I don't think it's very illuminating though, so let's just cut to the chase and give you the end result. It will be something that we can stuff inside our normal integral in the real numbers, right? So we're not quite dealing with an integral of vectors or anything like that. We just end up with this function, the square root of the partial derivative with respect to x. And this is just this one particular rectangle. So to get that one particular rectangle, we kind of have to note that we're working here with this point, which is located at x sub I comma y sub I. Okay, so in this formula for this particular square given by these two vectors, if you were to go through and do this process, which is, you can try it if you have nothing else to do, you'll end up with this f of the partial derivative with respect to x at that point squared, plus the partial derivative with respect to y at that point squared, plus 1, and then times change in x sub I, change in y sub I. I lost a bit of it. Then when you do the Riemann sum, well, you got it. It's just this thing right here turns out to be the kind of formula that you're using. And it's nothing special. We can handle this given our knowledge of how to integrate iterated integrals. Okay, so the surface area, and if you call, we're going to call this delta t, okay, for a tangent plane. So we got a bunch of little tangent planes on here, and the way the Riemann man adds these up, see, you can describe it with a bunch of different, with a sum of a sum, basically, is how they would do it in other books. So you would have a sum going in this direction, and then you need this row and this row and this row, etc. Okay, so the surface area at the end of the day, the Riemann-Man is adding up all these tangent plane areas, and then it's taking a limit to smooth it out, and what we end up with is a double integral over a particular region. So our region was a circular region here of this thing in green, dA, right? So if you want to write it all out again, so what is this? Allow me just to write f of x squared. Hopefully that's not confusing. Fy squared plus 1, and then dA. Whatever order of integration you want to do. Okay, so it's pretty cool derivation. Let's dive in and see if we can handle actually doing some of these exercises in the book. So the first exercise, find the surface area over the given region. This one's really easy. It's just the surface area of a plane. So our surface is 2x plus 2y. And then the region is a triangular region. The book will give you some ordered pairs, and you can draw out the triangle. Okay, so in particular then, the ordered pair 0, 0, 4, 0, and then 0, 4. Okay, that will be our triangle. And right, so we need fx. The partial derivative with respect to x is just 2. And then we need a partial derivative with respect to y, which is 2. And then we're double integrating over this triangular region here in the xy plane. And we need to plug in the square root of 2 squared plus 2 squared plus 1. Okay, so 4 plus 4 plus 1 will be 9. If you want to write it all out first, that's fine. And then times dA. So let's do dy dx. Okay. So we've chosen the traditional order of integration, and our Riemann going in that direction. So I'm going from y equals 0 to y equals whatever that line is. And then the Riemann is going from 0 to 4. So I have to figure out what this line is. Its intercept is at 0, 4. Okay, so y equals mx plus 4. And then at 4, 0, so when x is 4, when x is 4, y is 0, right? So you can plug that in and find the slope. And so our line is y equals negative x plus 4. Okay. So I'm going from 0, y equals 0, to y equals negative x plus 4. So I can put that in my upper bound, or upper limit on my integral. And then I just need to integrate that thing. I might as well do it. So this will be a double integral of square root of 8 plus 1 is 9. The square root of 9 is 3. You could pull any constants out of integrals, so just cut to the chase and maybe pull that guy out and have a 3 out, sitting outside. Dy dx, I need to integrate it, the inner part first. Okay, so with respect to y, that'll just give me a y. So 3 integral of y, I still have to evaluate it. Dx, evaluating from 0 to negative x plus 4. Okay. Then plugging in 3 integral negative x plus 4n for y. So I have negative x plus 4. And then minus plug 0 in for y. That will just be minus 0. So I won't bother with that. And then I have a dx. Okay. So finally, that'll be 3 times negative x squared over 2 plus 4x. And then minus, sorry, we're evaluating from 0 to 4. Okay, so this will be 3 times plug 4 into here, so you get negative 16 over 2 is negative 8. Plug 4 into here, you get 16, so plus 16. And then minus, plug 0 into there, you get 0, and then plus 0. Okay, so 3 times negative 8 plus 16 is 8, and we end up with 24. They can look pretty nasty. Let's look at one that's a little nastier. But usually there's a huge cancellation. So it'll seem like, oh, there's no hope, but then all of a sudden things will cancel out. Or if you just do maybe a polar conversion, a polar substitution, you'll be good. Let's look at what used to be number 11. Again, we're trying to find the surface area of this thing, the square root of x squared plus y squared over top of the region R equals the set of all points x comma y such that 0 is less than or equal to f of x comma y, which is less than or equal to 1. Okay, so this is really the z outputs for this guy here. What is this guy? Well, if you replace this with a z, and you look at this thing, it's going x squared plus y squared. And then if you square both sides, z squared is x squared plus y squared. And then you do some analysis like we did in chapter 11. You would find that this is an elliptic cone. And because we're dealing with the z equals square root of this, it's just the top half of an elliptic cone. Okay. If you restrict, so an elliptic cone looks like this, in case you've forgotten. Okay. Or something like that, right? The fact that it's a square root means that we disregard this bottom part here. And then this region part it's all the x values that have corresponding z values, where z is from 0 to 1. Okay, so that's kind of complicated, I guess, but really it's just saying so this is my z-axis. And I only want to consider z values that are ranging from 0 to 1. So maybe it would be this range here. Okay. So z is going from 0 to 1. So what you get is just part of the cone, right? So maybe you just get this part of the cone here. And you need to find the surface area of that. Okay. Okay, so you can determine the region you're integrating over is mainly just the projection of this part of the cone onto the xy plane. Okay, so here's the xy plane, and I want to project this onto there. So what you're going to end up with is a circle in the xy plane. Okay, so this is my x, this is my y. And I need to know the formula of that circle, and it may or may not be clear at this point, but it's going to be a circle with radius 1. Okay, so if z is equal to 1 here, in this formula, you get x squared plus y squared is 1, which is just a circle of radius 1 in the xy plane. Okay, so this turns out to be the region R that we're integrating over. In particular, you're going from 0 to 1. Okay. Okay, so we need to get the partial derivatives to pull this off. So f with respect to x of this thing, right? So its square root can be thought of as an exponent of 1/2. So you bring down the 1/2, then you have x squared plus y squared to the negative 1/2 times, and you have to do a chain rule. Okay, so the derivative of the inner part is 2x. And then the derivative y squared, because it's with respect to x, is just 0. Okay. And then clean it up, and you get x all over the square root of x squared plus y squared. And then fy is the same thing, except in the top you'll have a y. If you don't believe me, pause the video and go through it. Okay, so for our double integral, we need to form this big ugly thing. And the point is it's going to simplify. So if you square this, the numerator will be x squared. The denominator and the denominator of the square root part is going to go away. So you just have x squared plus y squared. Plus this thing squared. So in the numerator I have y squared. In the denominator, the square root part goes away, and you have x squared plus y squared. Plus. Then finally you'll have 1, right? That's just from the formula. And then we have our dA. Right, so then what? You can combine these, and look at that, it's almost like magic, right? If you combine the numerators over the common denominator, you just get x squared plus y squared all over x squared plus y squared. And then that thing is just 1. So you have 1 plus 1, in other words, root 2, and then you can factor the root 2 out of the front of the integral. Okay. And let's do this in terms of y and then x. It's kind of a traditional ordering. Here's the region I'm integrating over. So if you go y equals, and so the Riemann man is going in this direction. So y equals this curve to y equals this curve. Okay? And I can say, what is this? This is going to be y equals plus or minus square root of 1 minus x squared. Okay. That's the equation for the circle there, the top and the bottom parts. So I'm going from y equals this curve to y equals this curve. So y equals the negative square root of 1 minus x squared to the positive square root of 1 minus x squared. And then the Riemann man is going from negative 1 to positive 1. Right? So the Riemann man is running from negative 1 to positive 1. Okay. We could do this in, maybe I should have just went the polar. I'm sorry, I should have just went the polar at this point. Rather than having to do this integral, just do it in polar form. Otherwise, you can have to maybe, well, you can do geometry. So, so this would be the root 2 integral negative 1 to 1 of y evaluated on those bounds. So dx. And then you get square root of 2 integral. If you plug this minus this, it becomes this plus this. So you just end up with 2 square roots of 1 minus x squared dx. Then the integral of this thing is from negative 1 to 1 is just the area underneath this curve here, if you factor out the 2. Right? So it'd be 2 root 2 times the integral of the square root of 1 minus x squared dx. I mean, they would train you to do like a trig sub here, or we would normally do a polar sub, but I've sort of skipped that part. But what is this integral here? This integral is just the area underneath this curve here from negative 1 to 1. Okay, and what is this region here? Well, that's just a semicircle, so it's 1/2 pi r squared, where in our case the pi is the r is equal to 1, right? So it's just 1/2 pi. So this is 2 root 2 times 1/2 pi, and then times 1/2 will be root 2 pi, which is our answer. Okay. Okay, so there's multiple ways to do these integrals depending on your tool set. That's just another way you can pull it off. Okay. Let's take a look at another one. Just one more, and we'll call it quits for this video. Number 17. Okay, so in this case, we want to find the surface area of a partition of a sphere. Surface area part of a sphere. And the sphere is x squared plus y squared plus z squared equals 9. And then the part we want is the part inside this x squared plus y squared equals 9, which is a cylinder. Okay, so what do we have then? We have a sphere with a cylinder kind of zipping through it. Like that. And we want to know the surface area of the part of the sphere inside this cylinder. So the parts that are inside the cylinder are this circular region here, okay? And then there's going to be another one down here, which you don't see, right? Where the cylinder goes through the bottom of the sphere. Okay, so the way I approach this problem is to kind of find this surface area and then just multiply it by 2. Okay, so I need to figure out the region I'm integrating over. And also, when I go to my integral, I'm not going to be able to use this thing in terms of x, y, and z. I need to solve for one of the variables. I'll solve for z, so that will be the square root of 9 minus x squared minus y squared. Okay. And then this will be the region I'm integrating over. So if you kind of normalize this thing to the xyz plane, the region I'm integrating over will be this circle in the xy plane. Right? So the formula for that circle in the xy plane is that circle is this guy right here. Okay? And whoops, I made a mistake. This should be 25. Otherwise, it would be a different kind of problem. Right? So the radius of the sphere is bigger than the radius of this circle. Okay. So anyways, I'm going to need zx and zy, which looks like a nightmare. So zx is going to be 1/2 times 25 minus x squared minus y squared to the negative 1/2 times negative 2x. Right? And then that will be negative x all over the square root of 25 minus x squared minus y squared. And then zy is going to be kind of the same spiel, but with a negative y up top, right? So negative y all over the square root of 25 minus x squared minus y squared. Okay. And okay, I think I'm kind of ready. Maybe we should rewrite this thing. No, let's not bother. We're probably going to end up doing a polar substitution anyways. So we should be good to go. Right. Let's dive in to our integral. So here's our double integral now of the square root, and hopefully there'll be some cancellations. Probably not a lot, but this thing, this zx squared plus this zy squared will give me x squared all over 25 minus x squared minus y squared. The square root will go away. Plus y squared all over 25 minus x squared minus y squared, right? And then plus 1 dA. And then I have the double integral of x squared plus y squared all over this material. And what I'm going to end up doing is a polar sub, right? So you have x squared plus y squared all plus 1. And there's still one more thing I want to do before I go to polar sub. Right? I'm going to find a common denominator here and then add those two expressions together. Okay, so top and bottom here will be 25 minus x squared minus y squared. So you'll have x squared plus y squared plus 25 minus x squared minus y squared. And you'll just be left with a 25 in the numerator. And then the denominator, you have the 25 minus x squared minus y squared. Okay. And then you have your dA. Okay, now I want to do my polar sub. So the formula here for this guy is just going to be r equals 3. And then I have to let the running man go from 0 to 2 pi. So 0 to 2 pi, r is going from 0 to 3. And then inside my square root, I have 25 all over 25 minus r squared. And you always have to tack on an r dr d theta. Okay. I'm going to simplify a bit. So this, the square root of a quotient is the quotient of the square root. So I'll have a square root 25 over square root 25 minus r squared. I'm going to factor out the square root 25. That will give me a 5. And then I have the double integral of 25 minus r squared to the negative 1/2 times r dr d theta. Okay. And then I'm going to do a u sub on this character here for 25 minus r squared. So u is 25 minus r squared. Du is negative 2r dr. Okay, so dr, maybe I should do it over here. So u is equal to 25 minus r squared. Du is negative 2r dr. And then dr is negative du over 2r. And this then will give us, well, what? You know, it ends up giving us 5 times the double integral of u to the negative 1/2 times r times our new dr, which is negative du all over 2r, and then d theta. Okay, and then do some simplification. The r's divide out. There's a negative 1/2 that can get pulled to the front. So negative 5/2 now in front. And then I want to integrate this u to the negative 1/2. Okay, so that'll be u to the negative 1/2 plus 2/2 is u to the positive 1/2 divided by 1/2, which is the same as multiplying by 2. And I have to remind myself to evaluate. And then this will be negative 5/2, whoops, times 2, right? So let's just write negative 5. And then back substituting, I'll have the integral of 25 minus r squared to the positive 1/2. And I have to evaluate this thing from 0 to, what did we say, 3? Yeah, d theta. Okay, so this will be negative 5. If I plug in 3, I'll have 25 minus 9, which is 16. And then minus, if I plug in 0, I'll have 25. So 25 minus 9 is 16, but then I have to take the square root of it. So this first one will be 4. And then minus, plug in 0, so 25 minus 0 that is 25, and then 25 to the 1/2 is 5, d theta. So 4 minus 5 is negative 1, so if we pull that out front, I get a positive 5 integral d theta. Okay. And then the integral of d theta is just theta. I have to evaluate from 0 to 2 pi, which of course is just 10 pi. Okay. Okay, so then you look in the back of the book and you realize it's wrong, right? It should be 20 pi. So why is it 20 pi? Well, it's because I set up my integral just to find the surface area of this top region. You still need to multiply by 2 because there's also this bottom region in there too. Okay, so multiply by 2, and your answer is 20 pi. Okay. Okay. Thanks for watching.